All right, hey friends, and welcome to week 57 of Chill Kernel Hacking for Fun. Thanks for joining. Today is going to be a good week. Today we are moving on with the network driver and working on, the driver for the network interface card. Give me a couple moments just to get everything set up streaming wise. I'm multi-streaming to YouTube and Twitch for the second time. So let me refresh. Wait, I'll be right back. I think at Twitch. All right, test 1 2. All right, Twitch says we are live. Cool. Okay, that's better. Live on Twitch. Test Twitch to let me post in Discord. But yeah, today we're working on the network driver. I think this will be a pretty good stream. We will be doing some PCI stuff today, which will be new for me. So let me post ping in my Discord. Welcome to everyone joining. Hope everyone's having a nice Sunday. Okay, announced in the Discord. What's up everyone joining the stream? Yeah, we're gonna get into it in just a moment. All right. Hey Elote, welcome to the stream. Thanks for joining. Let's see, are we ready to go? I'm just gonna create a new workspace down here for today. Today is March 2nd and it's stream 57. And we are working on this part. Exercise 3 is today. One thing I do want to do, well, one thing that I've done in the meantime that I'll just show you is that I've actually switched to a version of qemu that I've built myself. Previously, I was using a qemu that I just got via Homebrew, which is pre-built. But in these labs, I'm going to want some of the debug logging that is available in qemu, right? And in the version of the class, they actually use a patched qemu that enables additional logging. And I think that will probably be pretty important for me. So if I want to get those logs, well, I actually tried using this version of qemu from the class, but the OS doesn't boot under it because it's a pretty old version of qemu. I don't really know what's the problem there. I also don't want to debug it, and so I'm just going to use a newer version of qemu. And that's what I have right here. Actually, no, it's not. This is the MIT one, qemu upstream. Here I have a fresh qemu, and I just built it, and we have some qemu binaries, but I don't think I actually enabled the PCIe logging. So that's going to be one thing I want to do today, and then we'll get into the stream. Is Miro better than Notion? Miro and Notion are super different things. Notion is kind of like a note-taking tool with like databases and stuff, and Miro is mind mapping kind of brainstorming tool first and foremost, but it also has a bit of shared functionality, but I don't even view them to be in the same category of tools. I like it a lot for what I'm doing here because it's very free form. Let's see, is the chat widget working? That chat widget does appear to be working. Good. And just a quick test, is the audio, my audio board.
This is a certified hood classic. Damn, son, where'd
I
you
think my
find
audio
this?
effects are working. So we are all set up to go. Let's get going with enabling the qemu debug messages for the E1000. I think actually this is the file. So what I want to do is, I think it's actually very simple. All I want to do is just define this actually. Hey Marcus, I am not going to MIT. The labs are public and anyone can access them, and I just posted a link. So yeah, I'm just a random person on the internet that is following along for personal learning. So all I've done is I literally just defined this define, which was even commented out, and that enables this whole set of logging macros. And then I can go into the build and just rebuild it. And that was very fast because I think it didn't need to build so much. Yeah, I don't really... I would expect one of these to be like the E1000 file, but it's not really that important. I wonder if there's an easy way I can test. Maybe I can look for this string E1000. Just out of curiosity, I wonder if that will work. Strings, just to confirm. Strings, qemu system, i386 ag. I see a couple of these defined. So let's just assume that works. And so now I've configured my tools. Yeah, I've configured the makefile to use my custom built qemu instead of the one from Homebrew. So I think that was kind of it actually. So I'm just going to go here and make a new branch, and I'm just going to commit enable E1000 debug logs. Okay. Cool. So maybe actually, and I can maybe even test that this works by running the examples, kind of test code from the previous exercise. So I don't see a line that says E1000, but I also don't know if we necessarily expect to yet, because there's no code in there yet for actually enabling the network card or anything like that. So yeah. Okay. Just checking in. How's Twitch doing? It's on got one person in Twitch. Yeah, I've been double streaming to Twitch, but because I thought maybe there might be some people on Twitch that are interested in watching, but so far not really. It seems like YouTube is the place to go. Okay. So what? We have some random junk that I was playing with. I'm going to commit the, oops. use my custom key with debug logging, and then I'm going to stash play some of these changes. Okay, now we are ready to get into it. What's up, Derek? Thanks for joining. Now we're ready to get into it. So I need a couple things. I need my documentation. Give me one moment. Okay, I'm gonna find that. My path is quite unique. Thank you. E1000 manual. Okay. We're probably going to need this. Yeah, hopefully you can read this. So what's the first thing we need to do? I did a bit of reading the manual last week, but it's really detailed. Okay, PCI interface, let's begin. The E1000 is a PCI device, which means it plugs into the PCI bus on the motherboard. What's up, Saksham? Thank you, appreciate that. Plugs into the PCI bus. PCI bus has address, data, interrupt, and interrupt lines. So the CPU can communicate with PCI devices, and so PCI devices can read and write memory. A PCI device needs to be discovered and initialized before it can be used. Discovery is the process of walking the bus looking for attached devices. Initialization is the process of allocating I/O and memory space, as well as negotiating the IRQ line for the device to use. Okay. Provided you with PCI code and PCI-C to perform PCI initialization during boot. The PCI code walks the PCI bus looking for devices. When it finds a device, it reads some IDs and uses these two values as a key to search the sum array, which is an array of keys and a function pointer. If the discovered device's IDs match an entry, we call the function pointer to initialize the device. Okay. The attach function is passed a PCI function to initialize. PCI card has multiple functions, although the E1000 exposes only one. Here's how we represent the PCI function. It has a bunch of stuff which I don't totally understand. The above structure reflects some of the entries found in table 4-1. Let's find table 4-1. Table 4-1. I'm going to screenshot this since it sounds like it might be important. Okay. Mandatory PCI registers. Interesting. Okay, there's some explanations. Have I tried eBPF? No, I've never tried eBPF before, actually. It's on my list. Okay, the last three entries are of particular interest as they record the negotiated memory I/O and interrupt resources for the device. The reg base and reg size arrays contain information for up to 6 base address registers. This was the base address for memory mapped I/O registers or base I/O ports. Reg size contains the size in bytes or number of I/O ports for the corresponding base values. Wait. For the corresponding base. So, okay, so for each possible base, we have some certain size from that base, which is valid. Presumably, if I'm understanding that right. IRQ line contains the IRQ line assigned to the device for interrupts. Specific meanings of the bars are given in the second half of table 4.2, which is here. All right. Expansion round. All right. I'll just screenshot this also. We got 15 people in the stream. Nice. Welcome everyone. Give a hand for yourselves for coming in on this nice Sunday. All right. Okay, so yes, when the attached function is called, the device has been found but not enabled. This means the PCI code has not yet determined the resources allocated, and thus the last three elements are not filled in. The attach function should call PCI func enable, which will enable the device to negotiate the resource and fill in the struct PCI func. Let's take a look. This is totally new stuff to me, so I have a lot of learning to do. I have never done PCI programming before. Okay, PCI func enable, PCI init, PCI scan bus. Where is this called from? It's called from init.c. Okay. And it has some data structures and it scans the bus somehow. So yeah, I did not write any of this code, just using it. And we got the test one from Afnan. What's up, Afnan? Okay. Attach match. So here's where it checks if the keys match and then invokes the callback. Conf set address. Let's just briefly explore how this works. So PCI init. Stay with it means. What about you? I'm good. It's always good Sunday when I'm learning about computers. Yeah, weather was better before, but now it's not so good here. So PCI bus, which is a pointer to a PCI function parent bridge and a bus number. Okay, PCI scan bus. Okay, broad strokes. What's going on here? Whoa, what? I'm already confused. We have a PCI func df. I don't know. Which we clear out to zeros. We set the member bus to this bus, which we've just initialized. And then what? I'm already confused. Okay, so we have an iterator variable. It's this device. So what's a PCI func with a device? So we are incrementing from 0 to 32. What's up, digitalized test 2? Thank you for the test 2. So we're iterating 32 times through 32 device numbers, I guess, and we are reading some. What's PCI con? We're reading. Okay, so we're using IO port IO to interact with something. PCI conf set adder. And this does what? Interesting. So it seems like to scan the PCI bus, we kind of we like have a bunch of information like the bus number, device number, function number, and all this stuff. And we pack it together into an integer and write it out to an IO port. And then conf adder, conf data. Then we read an IO port and see what that returns. And then that returns some data. And if it's greater than 1, if it's like 0 or something, or if it's 0, it's valid or something like this. So we've discovered, so it seems like we're kind of almost brute forcing the bus, basically. It seems like that's kind of how it works. We just sort of like have a bus number, and then we just brute force every device number and then see what the PCI, I guess the PCI root complex returns. And then from there we do func. So once we've discovered a device, we want to discover all the functions within a device. I think that's what this is doing. And we can read data. We can read data about a device function using PCI conf read, which is again this like core functionality where we write to an IO port and then read back. We like basically write into the IO port what we want to read, and then we read from the IO port something, and it returns us the data which we said we wanted. And then using that interface, we can ask for different kinds of information, such as the device ID. Interesting. Interrupt line that it's connected to or something. Device class. And then we attach. And then here's where we presume attach match. I guess here's where we're going to do some searching through our list of known, of kind of like the drivers that we're aware of, and look for devices that match, and then call the initialization function. Okay, I think that's enough of a high-level overview to continue with the lab. Implement an attach function to initialize the E1000. Add an entry to the array to trigger your function if a matching PCI device is found. You can use the vendor ID in section 5.2. You could find in section 5.2 of, okay, I don't know. Section 5.2 of what? Okay, I can find some IDs somewhere. You should also see these listed when JAWS scans the PCI bus when booting. Okay. So I'm going to do my very first baby step here, which is just get it to print out everything it finds. So I can't read. Okay, bus number, device, right? Function. I'm just going to print I'm just gonna print hello for my absolute baby step here. Now I guess I'm just trying to boot my kernel. Qemu. Does anything happen? That's a lot of code that's compiling. Hello, okay. Nice. You know, I don't really want to boot super far. I think I'll just add a panic into the init process. I think I'll just panic right here. Oops. No. It's kind of a problem that it compiles so much. I think it even is compiling every single time. Wow, that's annoying. Compiling every single time, which that's a problem. Like, it really should not do that. I think it's compiling the entire kernel every time I run the kernel, which it should know that nothing has changed, so it shouldn't do that. So that's kind of a problem. Anyway, the panic worked, and we are only printing this stuff. So, and actually there's already a bunch of prints. So maybe let's take a moment to even read these prints. PCI. Okay, maybe I should grep for. Okay, PCI print. Right, so these are the class. It's these class messages, right? And what are we seeing in these class messages? It's this incredible format string, bus number, device number, and function. PCI func. Function is an integer, interesting. So device, bus, okay, there can be multiple buses. Within a bus there are devices. Within a device there are functions. Okay, that makes sense. Next up, vendor and product ID based on the device ID. Next up, class and subclass. And then class is just a pointer to a PCI class, and then an IRQ number. Let's see what we see here. So all on bus 0, and we have some different device numbers. And then we have pretty rarely some different functions. Then we have our vendor and product ID, class numbers, a human readable description. Right. Human readable description string and IRQ numbers. Okay, and what we are interested in is the network controller, which has 3 entries here because for reasons I don't completely understand, there are 3 3 device IDs, all with a single function. And actually, even these 2 share an interrupt line. Actually, a lot of these are 0. I don't know what's going on with that. So that is interesting. Also, let's make sure our break time monitor is running. Okay. So we see some stuff. We can learn more about what devices we see from looking at the makefile, which is what invokes qemu. And actually there are, so we have this net command line, and then we have a bunch of forwarding that's happening. And I wonder if that's related to why we see 3 devices here. I will do a quick test. Let's say we only wanted to have 1 forwarding. Does that change what we see here? Ooh, printer type does not have value dump. What did I? Did I do something wrong there? All I wanted. So what do the command lines normally look like? Wait, so we don't, I think actually there's like a bug here, and there are a few of these backslashes missing even. Because right now it just has, it has 2 host forwards, which makes sense. It's actually missing this last thing. And it would actually even seem that this is incorrect. So if yeah, wait, so now we're going to do some yak shaving and figure out, I'm just going to search for this qemu. Or maybe I will just go to my qemu documentation. I actually have, wait, I saved links the first time. Or did I? Qemu docs network pcap. 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 Dump the network traffic. Dump. I believe this is the new syntax for it. Okay, let's just use it. So come back here. So this is not what we want. I see drivers I click. Catflare is a drivers kind of person. Filter dump qemu.pcap netdev u1. Okay, maybe it's time to just ask ChatGPT, because I don't really have the patience for this. All right. Let's bring in the LLM. Here's a qemu command line. The last line doesn't work. It's from an older qemu. What's the new syntax I should use to capture pcaps? Man, that's cool. AI is so good, man. At least let's see if this works. But I'm hopeful that it will. Okay. It's so unfortunate. Ooh. NetDev expects. Oh, did I? Ah, ooh, it actually told me what I should do. NetDev user ID. Okay, you know what? I'm just going to listen to it. Yeah, let's just blindly trust it. Yeah, I don't know why. Every time I run OS, the whole thing compiles, which kind of sucks, big time. But I just have never felt like figuring out why. But now the compiles are taking a little bit longer than I'd like. Okay, so now our qemu command line is fixed, hopefully. And we can actually see 4 entries for network controller. I wonder if that makes sense. If I comment out these, is there only one line? Yes, there's only one line. Okay, take a screenshot. Okay. Okay, but if we enable the forwarding, we get a new entry for every forwarded port. Man, I wonder how hard it would be to fix this OS compiling thing. That's really not what I wanted to do today, but you know what, maybe? Chat, do you think this is a good time to bring out the old cursor and just ask it to fix this? That would be pretty sick. I think I might want to try that. Okay. Temp panic. And we don't actually need this anymore. And I'm just going to okay. I am interested enough to maybe get cursor going in here, verifying cursor. So here's what I want to do. new window. All right, we're gonna see how well this works. I have cursor here, which I was playing around with. And in general, I've been trying to not really use AI like too heavily for my project, but I think this would actually be a great use of it. New chat. So let's, every time I run make qemu to run my OS, it recompiles the whole thing. Can you figure out why and fix it? And I've just been hearing that Sonnet 3.7 is super good. Okay, we're gonna let the AI, oh. All right, what does it say? Let's clear out some other files though. So, what does it say? Blah, blah, blah. The warn target is referenced in the all target, but isn't defined. Oh, that actually might be it. Damn. Make sure. But what is warn? I don't understand. The qemu target depends on images. You know, I'm just going to delete the warn. That's some dumb warning from the class. Okay. But what happens if I have an empty all? But also, it doesn't matter because I'm not using the default target. I'm using the qemu target. But actually, just out of curiosity, if I just do make, so just a raw make, and if I do that again, yeah, so just a raw simple make is recompiling every single time. All right, let's add the warn back, and let's add a warn here. I don't actually expect this to really do anything. Make. Yeah, it's still recompiling everything all the time. What's up, Ismail? Welcome to the stream. So am I keeping track of dependencies? I know very little about this, but I thought we do because I'm not sure actually where you saw this, but in our C flags, there's some specific C flags that I think the MD C flag is the one for dependencies, right? I think. No, that's the native. Yeah, MD. This is what we're talking about. So we can just take a look at the object dir. For example, kern, right? So I have all of these .d files, which are those dependency files. So that's why I thought it should not recompile every time. The main issue is that all depends on, okay, that's fine, but okay, all. I don't know, does it need to be above here? Make. Right, so now we're getting the warn target, which is kind of stupid because now I can't compile it. So I'm not sure how useful that was. So I'm going to delete all. Okay. Deleted the warn target. What about now? I see the issue now. Wait, what's the issue? Warn is still referenced from the phony list. Uncomment and implement the warn target. What if I just don't want the warn target? I swear if that... So, build. I think nothing changed. I think, yeah, it's still doing it. Warren? This is insane. Okay. What is the default target? I wish I knew. How do you even find the default target? Yeah, this is what I'm talking about. This is annoying to fix. It's like, I guess what happens when I compile? It just like builds the OS. Kern make frag. MMDMP, interesting. Objders, LD flags, kernel, targets, all. There's a second all here. Is that right? How many? Ooh. How many alls are you supposed to have? Are you allowed to have? I have actually 2 right now. What if I comment this out? Make. Okay, so now it this is a replacement for MD. Are you moving OS image after building? That is a good question. All right, we should set a time limit for how much time we're going to spend on this. How much more time should we give it? I would say if we have not solved this in the next 6 minutes, we're going to stop. Okay, 6-minute timer. Okay. Okay, so I think this all was actually important. I'm looking for move. What if I specifically try to build this obj or kernel image thing? Make obj kernel image. Right, it builds it. And then just does it again, right? So there's something wrong here, so maybe we can recurse. What if I try building these dependencies, like kernel, okay? So I'm kind of recursively going down the targets. All right, 20-second break, be right back. So recursively, so building this kernel target does it. So what's going on with the kernel target? Kernel obj files, kern bin files, and this thing. None of these things should change. But wait, weren't we supposed to be asking AI to fix all this? What did it say? That didn't work. Whenever I build specific targets, even like obj kernel, it still rebuilds every time. Can you see something wrong with the kern makefile? Great, lib. Okay, so it doesn't know. Damn. But even we've like narrowed it down to quite a specific thing here. What also? What's up with this? What's up with this thing? I don't trust whatever that is. Okay. Does the build still work without that? It still works. It still seems to work without that. Make kern.ld. Oh, hey, this is stupid because it's just a static file, so there's nothing to be done, obviously, for that. How can I get more? But wait a sec. Maybe I will just spam some C flags, right? Also, wait, what are we seeing in the C flags? Are we seeing the -m? -md. All right, I'm gonna try Ismail's. Or maybe I'll ask, is a better way to generate dependency info than how I'm doing it now? Okay, let's just do it. So right, and here too, why not? Okay. Kernel. And it's still doing it. That is so frustrating. How do I comfortably use this keyboard? This is incredibly comfortable to use. so comfortable that I actually ditched it from this other keyboard that I was using, which was like this ergonomic bigger one. I am really enjoying this smaller Apple keyboard. Okay, that did not work. Something's going wrong, and I think the timer went off. So let's unfortunately just accept the fact that that is going to be very annoying, and I'm just going to yeah, just delete all of, maybe I'll stash this, build, fix, try. Okay. Too bad. I had high hopes for cursor for that one, but that didn't work, so let's keep it moving. So we were just trying to see if what's going on here. So now we have 4 network controllers, each with a different device number. It sort of seems like we have 4 different NICs plugged in here, actually, which I'm not sure is what we want, but maybe that's just how this works. So I don't know. Okay. Okay. So let's code. Implement a function to initialize this. Add an entry to this to trigger a function if a matching PCI device is found. Okay, let's just go. So we're looking for the PCI attach vendor, right? And we need some vendor ID, which is this, I think. It's 8086 1000E. Wait, is that hex? Yes, that's probably hex. Okay. Of course it's hex. Hex, hex, and Nick attach. We'll just call it this. I don't know. Actually, so do we have E1000? That's actually probably not a great name for it. It should be called E1000 attach, which we now should make. So void E1000 attach, and right, what are the okay, here's the function. So it's an int and then a struct PCI func pointer. Okay, int. So this is now going to include, and how do we include current PCI.c. Func, something like this. And now we want to use this definition. Wait, what? Okay, something approximately like this. We have an attach function, and I'm just going to panic. Panic on E1000. And hopefully we will see the kernel panic. Oops. When we, oh. I need to, where is panic even? Wow. Panic, oops, panic. Assert.h. But that's actually not here, that's in here. Wait, this is so strange. Okay, wait. Wait, what? this include, okay, whatever. Does it build now? Okay, so that built. We never panicked. Why not? E1000 attach. So that's already not great. Takes in a list. It's probably something very simple. Wait a second. Let's vendor ID. Ah, wait a sec. What is going on? So how does this match work exactly? We get two keys, and we just see that and we just check if the thing in the list is equal. And then we print, we got a match. Okay, so I'm just going to print out every comparison, I think. Right. And then let's print out the keys. Okay. Oops. Wait, what am I doing? Wait a sec, what? Okay, I am absolutely losing my mind. I did this completely wrong. So, key 1, key 2, I, D, D. Okay. But probably hex is what I want. Okay. We are slowly making progress. $100E. Okay, so that was me not being careful. Of course. Okay, so what's up, MD explains? Hello. Okay. Panic, I need attach. Okay, good. So that was kind of unfortunate, but now we're getting in here and we are successfully panicking. Having fun with circular queues. Not yet, but maybe eventually. So now I'm getting, find the vendor ID, action 5.2. Just enable the device via PCI func enable. So what does that mean? PCI func enable. Yes, it's the MIT documentation for this, exactly. Yep. So how do you enable a function? You can write a configuration, right? This is the same thing we've been looking at. There's this there's like this specific IO port, which is actually hard coded. Configuration mechanism. So yeah, you address and data, interesting. So these are hard coded IO ports. Okay. But this is a conf write actually. So this is the opposite. Well, it's actually similar. You set an address, and then you either read or write to the IO port. Interesting. And here it is populating the function. We can see that it's getting, I don't know, a region for memory mapped IO. Okay, so these are like kind of, okay, so we can see that, okay, we're initializing this PCI function. Not quite sure what this is, but map type, we are basically checking, is this PCI function going to be using memory mapped IO or port IO? I think, yes, that's roughly what's happening there. Okay, so let's just, so now we're going to depend on pick, and we're going to call pick, no, not pick, PCI. Oops. Okay, And let's just see what happens. It says this thing is enabled. Very cool. So that was super easy because they wrote all the code for us. But we have successfully enabled the PCI device. And all that means is doing a bit of configuration. PCI command status reg, enable IO, enable mem. And so these are, I guess these are constants. Maybe these are in the PCI standard or something. Yeah. Command status register. Okay. So we communicate to the PCI root complex or something like this that we intend to enable the device. All right, yo, I'll be back in 20 seconds. Feel free to get some water. Take a break. What's up, Bri? Chill version of Tokyo Split. That's the goal. That is absolutely the goal. All right. So we do some communication to enable the device, to communicate with the root complex that we want to enable this device. And then we read. And again, there are some kind of magic constants. Base edge register width. Yeah. Bar width. We write 1000 for some reason. Yeah, cursor would be good to. Yeah, thanks, Bri. R value, reread some bar. So the return value here has a bunch of information, apparently. It contains information about the type of the communication mechanism, like is it memory or is it port IO, which is probably a single bit. Yeah, it's just the first bit. This is like some bit mask, right? It contains information about the type and actually the base address and the size, which we're getting right now. And it's just, I don't know what old RV is. But yeah. So anyway, that seems to be how you enable a PCIe device. Okay, blah, blah, blah. You should now pass the PCI attach of make grade. So now we're getting into grade lab 6. And dang, okay, so I'm going to comment all this out. And I mean, it's almost not even worth really running it. Grade lab 6. Okay, that took a long time to compile. Now it's doing the time test. That was from last week. Oh, it failed because I have my custom panic in there. Okay, so that actually succeeds. Okay, so good. So that's a nice and easy start into lab 6. What was exercise 3? Enable the network the NIC PCI device. Okay. Memory mapped I/O. Software communicates with the E1000 via memory mapped I/O. Seen this before. Negotiates MMIO region and stores its base and size in bar 0. This is a range of physical memory addresses assigned to the device, which means you have to do something to access it via virtual addresses. Yeah, we need to map it. Yeah. Since MMIO regions are assigned very high physical addresses above 3 gigabytes, we can't use kaddr to access it because of JOS's 256 limit. Okay, that's where things start to get annoying. So, ultra quick illustration of this. So we have physical memory. So our kernel is mapped in kind of low memory at the 1 megabyte range. And apparently all these PCI stuff is like very high in physical memory. In the physical address space. I think the confusing thing is that, so RAM is kind of just here though. No. So RAM is some kind of small amount here. And this is physical memory. And then virtual memory, on the other hand, is over here. And the some like region of virtual memory is mapped for the kernel. I want to say it's 256 or something. Yeah, 256 megabytes of virtual memory is mapped for the kernel. And I think some subsection of that, like, so we can access comfortably like the bottom, I don't know, 128 or some amount of physical memory, but we cannot directly access but this super high these super high physical memory addresses are not available in our kind of mapping. Yeah, this is similar design with ARM also. If you open any ARM sock DTS, you can check the actual register regions. Also, what's up, Shivang? Been a minute. Ismail, plans for after the course. I would love to start working on my own OS, which I actually wrote code for. And I don't know, maybe re-implement a bit of JOS, but in my own style, or focus a bit more on drivers. Yeah, that's my general idea. Yeah, so our kernel, some limited section, limited bottom part of physmem is available here. And so it's saying we need to make that region available. You can't access it using kaddr because of JOS's 256 megabyte limit. Thus, you have to create a new mapping. Use the area above MMIO base. Okay. Back to the classic memory layout. We have this MMIO region. And this makes sense to keep using. And this is for memory mapped IO, which is not available through the normal remapped physical memory region. You know, this is actually interesting. Kern base starts at 256 megabytes from the top. So, and then there's even a bit more kernel memory below that actually until utop, which is right here. So there's kernel, so there's like the physical memory remap all the way at the top, and then a bunch of extra kernel memory below that. Yeah, 64-bit mode would be great. I feel like until you have, yeah, like you're not really doing it unless you have unless you really got to 64-bit mode. Yeah, then it becomes real. Until then, you're just kind of playing around. No, I actually haven't really started my own OS yet, but that's probably what I kind of would do. You want to record the location of this mapping in a variable so you can later access the registers you mapped. Take a look at the laypick variable as an example of one way to do this. If you do use a pointer to the device register mapping, be sure to declare it volatile. Otherwise, the compiler is allowed to cache values. Okay. So we have a PCI function, and how does one access the PCI function? We get it passed in here, but PCI func, right? Multi-func, crazy. Where are these stored though? This is just on the stack. So this is scan bus. Okay, that is Maybe a pointer gets stashed somewhere, or maybe I need to do this. No, that like seems a little bit silly, but maybe that's actually what needs to happen. Maybe I get ownership of this PCI func. Is that how that works? Because then attach is called, and the function that's passed in here is forwarded into here and passed into the callback. And so, but the thing that's passed is a stack variable. It almost feels like we need to make a copy of this, otherwise it gets destroyed. Okay, so time to actually do some thinking. It says to take a look at the laypick variable as one way to do this. Okay, let's take a look at laypick. So in the laypick, it does a similar thing. I guess what is the goal of this function? I guess we're gonna just do more stuff here. What is that? So with the lay pick, it's somewhat similar. We have some global variables. And then we map that physical address to a virtual address. And then clients can do reads against it. So that is, and I'm just curious, what these helper functions are just light wrappers of doing reads against that virtual address. So I think this is not maybe ideal, but this is one way to do this. So just to keep sketching it out, we have this PCI func, which we don't own and which will get destroyed, but which we have like a opportunity to read, basically. And in this